the organizers, and including Jifun. I'm one of the groups that benefited from this Agora comparison, and I'll show you an example how a small group like mine can benefit from the platforms such as Agora. But the main topic of science is a little different, and I'm going to talk a little bit about the large Subaru PFS survey that's going to come online in a few years, and what can a theorist can do for these such surveys. So the topic is about probing distribution of gas and galaxies and metals. So here's my collaborators. So I'll tell you a little bit about IGM tomography for those of you who don't know about this at all, students. And then I'll talk about simulations like other people. So some of you probably heard about this Laminar forest before. So typically you have a quasar around redshift 3, and that quasar spectrum travels through the universe. And then as the light travels through, at each redshift, there's some neutral clouds on the way. And if your wavelength matches up the 12-16 angstrom properly, then it will give you this absorption and eats up, and then it'll cause this honeycomb-like forest feature. But now the thing is that the quasar number density becomes a little low as you go to high redshift. So the idea came up that if you can use the star-forming galaxy as a background source instead of quasars, it may actually improve the sampling chance than just quasars. So this is an idea. If you can have these multiple sources, then you can have a lot of these line of sights. And the number density is demonstrated here. Here's a number of sources brighter than certain magnitude, and as a function of limited magnitude. And as you see here, as you go to higher and higher redshift, the quasar number density plateaus and goes down. However, if you look at the Lyman break galaxy, it increases quite rapidly. And if you can probe down to 24th magnitude at this redshift range, then you can have this number density. 0.4 arc square minute, and if you have a PFS field of view, you can get 2,000 sources in this particular field. So that's the idea. And if you have a cosmic web of gas like this, and instead of just having one quasar, you can have multiple sight lines through the star-forming galaxy, then you can probe the cosmic web much better. Okay, so that's the idea. And this has been actually already demonstrated by the Keck Telescope by K.G. Lee. 2014, he actually used only 24 star-forming galaxies at this redshift range, and already have shown that you can actually get this three-dimensional distribution of H1 density contours, although it's still on this limited spatial scale. And he's proposing a next survey called Collaborators survey with these specs. If you can probe down 23 magnitude in G-band, eventually if you can probe on 1 square degree, we can get this number of star-forming galaxy with this resolution. So with a spatial resolution of a few megaparsec, you can actually probe the large scale distribution of H1 gas density, and that's what we also like to do with a large survey. So Subaru is performing this Simulate project right now. It's a two-phase project. It's 5+5-year survey program. And of course, large field of view is the advantage of Subaru telescope over the others. Right now, it's doing the imaging survey using the hyper-supericam survey and collecting lots of galaxies. And it'll go to until next year. And then next phase is the spectroscopy, which is called the PFS survey, prime focus spectrograph. And it will have this number of optical fibers, and it will collect a large number of galaxy spectra around this time range. About 300 nights will be devoted to SSP special program. So we're discussing what we can do, combining these two large data sets and utilizing this, for example, for IGM tomography. Okay, so here's additional PFS parameters, 2,400 fibers, this field of view, and it will have this coverage of the wavelength, okay, with a moderate resolution, spectral resolution. Okay, so the science case includes the H1 tomography, as I just said, like the one that's discussed here. Next one is actually you can look for protoclusters at the same redshift range. People have been trying to find protoclusters through the galaxy distribution, trying to find like Lyman alpha emitter concentration or LBG concentration, but those surveys may be biased. Okay? But this H1 survey is less biased, so you can actually try to look for unbiased search of protoclusters. So this will be done also. And then the third topic, which I'll focus on today a little bit more, is to look for the galaxy H1 or the metal cross-correlation and try to learn about the relative distribution of gas and the galaxies and the metals, for example, hopefully, and learn how the galaxy actually form out of those cosmic web, like the ones you have been discussing today for the cold flows, etc. Okay. So also quasar H1 cross-correlation is already demonstrated by certain people from the BOSS survey, and so these are also another topic for cosmologists. Okay, so one topic that many of us have been interested in is the chemical enrichment of the intergalactic space. If you don't have any feedback, you actually don't enrich the intergalactic space, and that is obviously a wrong universe because we know IGM is enriched to certain levels of metals. But for benchmark comparison, the Springer-Hörnquist 2003 models that many of us have used over the past 10 years, this strong wind feedback is known to be overdoing the enrichment. You overheat the intergalactic media space, and you over-enrich the intergalactic space, and this is clearly too much. So the correct universe seems to be somewhere in between these two phases, and you have to do a moderate enrichment, not to overheat, but not to enrich too much IGM. So that's been done, for example, with the variable velocity wind models, which may depend on both energy and momentum-driven wind models, such as this one you see here. Okay, so these are the feedback, and it's actually fairly subtle. You cannot overdo it too much. So these things can be probed by these surveys. And a very nice data set recently came out from the Keck. Again, this is the KBSS, Keck Baryonic Structure Survey by the Caltech group. And they have already gotten this two-dimensional velocity structures of the H1 distribution around the galaxy. So this is a galaxy H1 cross-correlation in two-dimensional direction. So you have a galaxy here, you have a quasar, you have a nice spectrum along the way, and you know the transverse direction. You also know the Hubble distance. If you have a very good redshift constraint on the galaxy, then you can get this observed constraint on the three panels here. So this is H1, carbon-4, and silicon-4. Okay? And you see a hint of this finger of God effect, elongation on the vertical direction. And on the right-hand side, there's a comparison to the simulation, Eagle simulations. And by looking at this, you can actually see that the halo mass of about 10 to 11.5 would be the suitable comparison to the observation. So you can also constrain halo masses this way as well. Okay? Although we actually don't know yet whether this finger of God is produced by inflow, outflow, rotation. There are many possible dynamical effects that may cause that. So that cannot be disentangled at this point, but this is a nice example of demonstration. Okay. If you project that onto certain axes to look at it more carefully, to quantitatively, you'll see that each of the optical depth for H1, carbon-4, silicon-4, they all die down around physical 1 megaparsec or so. So in order to prove these correlation with galaxy, you have to have a resolution down to physical 1 megaparsec or 2 megaparsec. And if your resolution not so good, you won't be able to see this. So this is really on the edge of the resolution limit that PFS can do due to the fiber resolution. And that's a little bit of a dilemma for us right now, but that's what we have. Okay, so here's a demonstration of that. You have an estimated PFS exposure time as a function of the 3D tomographic resolution. If you observe down to the magnitude limit of 24.42 magnitude, you get a transverse resolution of about 4 megaparsec or so. Not that great. We cannot do metal, but only do H1. If you go a little deeper and look at 24.7 magnitude, you can actually reach to 3 megaparsec, and you can barely see this correlation with metals. If you can invest a little bit more down to 25th magnitude, we can get 1 megaparsec, and we would like to get to that at least one point in our survey. So that's the kind of things we're discussing right now, and come up with a survey strategy, more sufficient one. What other physical properties can we probe? For example, here's another example by comparison to the Eagle simulations by the Turner et al. Group. So here's a C carbon-4, silicon-4, oxygen-6. And by comparing these optical depth, this pixel optical depth of carbon-4 versus tau H1, they actually argue that simulation completely underpredicts the carbon-4 optical depth relative to this H1. So these things can actually tell us about the incompleteness or the weakness of the feedback models in our simulation. So for example, different models of the ionizing background radiation might be the right answer, or we need more resolution, or are we missing some kind of more broadening due to the unresolved turbulence, or the elemental abundance may simply be wrong. Okay? So these are things that we have to consider on top of what we have right now, and it's not that the current simulations are all correct and everything's fine. Another thing is outflows need to entrain more cold gas with metals, so there's another possibility. And these observations can tell us about these details of the feedback processes, and that's why it's useful to constrain the feedback models. So in my group also, we've been using Gadget 3 with some additions and modifications, updates on SPH, time step, viscosity, and all this, and also the feedback models. So as a simple comparison, I'll just show you a preliminary comparison of these three cases with no feedback. Canonical, the constant wind velocity that I showed you, Springer-Hörnquist 03, and then the recent model that we've been doing, which I call Osaka model, with some of my postdocs, with the updated cosmology and preliminary cosmological test simulations of the moderate resolution. Okay, so it's not that important here, just a test. One important addition that we lately doing is that the update of the chemistry. So we use this CLIB package, chemical package by Saito, and this allows us to actually implement the time-dependent yield, different yield of the type 1A and type 2 and AGB star contribution. So it has this stellar age dependence for each of these components. Therefore, we can have implication of these time delays of each feedback components. That's in order. So here comes Agora. We actually test these implementations based on the Agora isolated galaxy simulation that we've been making efforts past few years, and we benefit from this initial condition. So for each of the models, we ran this Agora isolated galaxy and see what kind of models are the best fit. And you clearly see that if you don't have any feedback, it does a very bad job. It actually fragments and forms lots of clumps and not very good models. If you only have early stellar feedback only, that's also not sufficient. It actually is very similar to no feedback case. Springer-Hörnquist also is not so good because it's kind of just blows out the gas and doesn't affect the disk ISM, and because you turn off the hydrodynamic force for a while. And if you have type 2 supernova and the early step, all the combination, you form a nice sort of smooth, nice spiral arms, and they seem to behave well. Okay, so this is kind of things that you can do with Agora setup. Okay, so once you have all these models set in, we do this cosmological work, and we manage to have this very moderate feedback. It's not that dramatic, but if compared to no feedback case, you see a moderate amplification of the temperature heating and enrichment. Okay, so in order to compare to the actual observation, you have to produce a line of sight. So we do standard practice of producing a light cone output. So we do 100 megapascal box simulation. You rotate and then randomize it, and then you stack them up and you produce light cone from ratio 2 to 3 or so, and then produce this optical depth distribution, which may depend on the H1 distribution, peculiar velocities, and temperature distribution. And you see that this, for example, this optical depth peak is actually slightly offset due to the peculiar velocities. For example, you have these shock features, redshift and blue shift collides, and that's where the temperature is hot. And these places actually, you see these offset on the optical depth. So you have to generate this, and you actually convolve it with the galaxy spectrum to produce the realistic spectra. Okay, so once you've done that, you can actually look at the cross correlation between galaxies, H1 for example, and you see we also reproduce these finger of God-like features like the Turner et al. Saw on the similar scales of 1 to 2 megaparsecs. Okay, so this is preliminary result, and we can compare these different models and see how much difference it makes on these feedback recipes. And you see some hints of this difference. So if you probe down to 3 megaparsec or so, you might be able to distinguish the difference of these feedback processes. Okay, high optical depth systems versus low optical depth systems. They also show the different positive correlation versus negative correlation, and you can probe the difference in the galaxy neutral H1 distribution. There's also a strong redshift effect as you go from high Z to low Z, from redshift 3 to 2. Even just a small redshift path, you actually see a strong evolution in correlation function. This is because the average transmission tau is actually decreasing as a function of redshift. So as you go to low Z, effectively, the high tau systems will be more biased as you go to low redshift. So this is what you're probably seeing here. On the other hand, a complete opposite. If you go to look at the low tau systems, lower column density systems, it's more outskirts of the galaxy in intergalactic space. Therefore, you actually see anti-correlation with the massive objects. So these are things you can see. And then likewise for the metals, we also do the same thing for metals, galaxy metal cross correlation. Although here we actually don't see a very strong finger of God effect. We still have yet to understand this. We need to do more analysis, but it's interesting that we don't actually see so much. And then you see similar cross correlations differences. If you probe down to 1 megaparsec, you can actually see these variations in the region of the space or the types of systems that you may have. Okay, so that's the thing that we like to do. And finally, I just want to show you one or two slides about the dust, because if you've done the gas with this tomography effect, you have the galaxies, you can have dark matter recleansing, and then finally one more thing you might want to probe is the dust distribution. And people are beginning to actually get intergalactic dust distribution, some data from the MG2 systems, for example. So we also recently implemented in this paper the very simple two-component dust model, modeling the entire dust distribution with the two-component, large grains and small grains. We actually follow the formation and destruction of these dusts on the subgrid level. So on each gas particle, we actually track the distribution of the large and small grains. So you see, as the isolated galaxy evolves from t equals 0 to 5 gigayears, you first form the large grains from the supernova explosions, and you release them with the feedback. And then as the large grains are actually shattered by the collisions, then you actually start to form the small grains from inside out. And then later, these small grains again accrete the gas from the nearby gas, and then later grow. And you show this, you get this nonlinear evolution of dust to gas ratio as a function of metallicity. So as the galaxy evolves, we see actually this nonlinear evolution, and then this nicely fits the observational data points as you see here. And this way, we can actually address the spatial distribution of dust evolution. For example, so we can actually compute the extinction curve as a function of radii within the same galaxy, or the time evolution, or density dependence, or metal dependence. Those details can be analyzed in terms of in comparison to the dust observation. Okay? So there's one movie also implementing this to the cosmological simulation at the same time. So not just isolated galaxy, but we actually implemented the same model to the cosmological run, and we're now testing these models. And so you can see on the cosmological volume of 50 megaparsec, you actually see this formation of large grains, more distributed than the small grains, more concentrated towards the galaxies. So these differences can also be analyzed and compared with the actual observations. Okay, so here's a summary, short. So PFS survey, it can be read as a precision formation of structures. This is just a joke, but I think in terms of the reproducibility that Jifun also talked about, we want to reach towards this precision structure formation paradigm using the simulations. I think we're on the good path for doing that. And this topic can actually give us a very good probe of baryon distribution. And in comparison, we can do the galaxies, metals, and dust, and dark matter at the same time to get a comprehensive picture of the overall universe. So along the details, we actually have to still do the photonization calculation for metals. So this weekend, we'll probably discuss more about this Trident package that the Cameron is developing. And I hope to do this more ionization calculation for these metals and refine it to become more accurate calculation. And then that allows us to do the more simulation of the PFS survey and then develop more better survey strategy. Forecast-based papers in preparation. Okay, thank you very much. I'll stop there. Yeah. Well, so if you look for clusters based on the stellar light, for example, around the quasars, there's an effect known as a LBG-LE segregation. So sometimes you see the LBG, sometimes you don't see Lyman alpha emitters. So if you just use one population of sources, you might not find the protocluster in certain region. Okay, but if you look for the protocluster in the H1, it'll be less biased. You're just looking at the overall baryon distribution. Okay, unless they are significantly ionized and you don't have any H1, then you won't miss it by this technique. So you get the more overall broad distribution of H1 more reliably than just losing the Christmas tree lights. Basically, that's all I'm saying. You can actually look at the trees instead of the lights on the trees. Yeah. Mm. Where do I expect the correlation to end? Okay. Well, in the simulations, we don't have the quasar, so I can't really make that prediction right now at this moment. I need to go back and look at this Font Ribera paper. There's a paper that from the BOSS survey, and I don't know. I can't remember the number of that. Yeah. Maybe. Yeah. Sure, of course. Right, yeah. So at the moment, our discussion haven't deepened that much yet. I guess if somebody's interested, I think we're welcome to look at it. But yeah, but yeah, sure. I think I in fact, Jason is becoming a member of IPMU recently, so I think he'll be participating in that aspect. Yeah, he already came one of the internal collaboration meeting, and yeah. Okay. Thank you. Yeah.